Weathering processes. Objectives. After attending this lesson, the user would be able to know the mechanisms of weathering that are responsible for the dynamic changes of landforms and relief features on the surface of the earth. The kinds of weathering, their impacts on rocks and minerals, and their role as geological agents are also highlighted. Introduction. The Earth's lithosphere is composed of varieties of rocks and their related relief features. Relief features are distinct landforms depicting the nature parent rocks and the geological processes that have created them. Landforms, their origin, their dynamism and distribution are studied in Earth's physical sciences under the branch of geomorphology. The relief of any land is not permanent on the Earth's surface. Every block of rock is subjected to aerial actions and modifications. Over a period of geological times, these surface blocks and rocks break down into smaller and finer pieces and move away from their sources. Since the rocks present in the uppermost layers of the Earth's crust are in close interaction with the processes of atmosphere, hydrosphere and biosphere, they are dynamic features. Geomorphic processes. The sun's radiant energy, role of water of the hydrological cycle, role of oxygen and carbon dioxide of the atmosphere, and the action of organic acids over the rock masses play a significant role in the material transformation over the surface of the earth. All the rocks exposed at or near the surface of the earth are subjected to various physical and chemical processes. These rocks are mostly unstable and are attacked by aerial agencies both physically and chemically. The processes acting on the surface are called as geomorphic processes. The notable processes are weathering, mass wasting, erosion, transportation, and deposition. In this lesson, the mechanisms of weathering and their impacts on the rocks and relief features are highlighted. Weathering. Weathering is an important geological mechanism which can destabilize the Earth's surface materials and remove them by erosive processes. Weathering is the physical disintegration and chemical decomposition of a rock mass on the land. It is a unique phenomena happening on the Earth's surface. Weathering is a collective term used to denote the mechanical, chemical, and biological organic processes that take place on the Earth's surface. Weathering of rock-forming minerals can create new products from pre-existing rocks. In many regions, soils are the ultimate products of weathering. Weathering of rocks releases chemical compounds that become available for biological processes. It is necessary to study the factors that are influencing the weathering processes. Factors influencing weathering. In simple terms, weathering is defined as the natural breakdown of rocks into minor fragments, soils, and sediments. There are many factors which influence the weathering of minerals and rocks. They are topography, climatic conditions, temperature and humidity, physical characteristics of rocks, chemical and structural characteristics of rocks, their mineralogy and structural features, and vegetation, their abundance and type, including the micro and macro vegetation. Weathering involves no moving agent of transport. Impacts of weathering. The impacts of weathering are very phenomenal. The nature and magnitude of weathering differs from place to place. The first impact is the physical modification of pre-existing rocks. Several modifications are made on the pre-existing rocks by mechanical forces, chemical reactions and biological interactions during the process of weathering. These changes are expected in the pre-existing geologic materials that are exposed at or near the surface of the earth. The second impact is destabilization of masses. Weathering destabilizes the surface materials and encourages their removal by erosion. Erosion is done by geological agents like running water, wind, glaciers, and water waves. The third impact of weathering is the formation of soils and sediments. The soils are the products of weathering. Weathering creates both soils and other loose rock fragments. The fourth impact of weathering is the chemical modification. Weathering releases several chemical compounds from the parent rocks and leaves them to support the biological processes. Types of weathering. Weathering is a general term for several processes. In general, weathering is of three types as physical weathering, chemical weathering, and biological weathering. The chemical and physical weathering often go hand in hand. Physical weathering can occur due to temperature, pressure, frost, etc. Living organisms may contribute to mechanical weathering as well as chemical weathering. Lichens and mosses that are growing on bare rock surfaces may create a more humid chemical microenvironment. The attachment of these organisms to the rock surface enhances the physical as well as chemical breakdown of the surface layer of the rocks. These are all very slow and silent processes. Physical weathering. Physical weathering is also called as mechanical weathering. Mechanical weathering is related to the physical breakup of rocks into small pieces and fragments. In physical weathering, there is no change in the chemistry of the parent rock. The physical characteristics of rocks also influence the process of physical weathering. The characteristics are differential composition, particle size, the hardness and degree of cementation. Some rock bodies are very resistant due to their strong physical properties. They may not be attacked by physical weathering processes. The structure of rocks are fully favorable to weathering activities. Presence of joints in rock bodies are typical examples. Chemical weathering. Chemical and structural characteristics of minerals present in rocks are also expected to play a significant role in weathering. Chemical weathering changes the composition of rocks, often transforming them when water interacts with their minerals to create various chemical reactions. Chemical weathering is a gradual and ongoing process as the mineralogy of the rock adjusts to the near surface environment. For minerals of given particle size, chemical and crystalline characteristics determine the ease of decomposition. Example, gypsum, sparingly soluble in water, is dissolved and removed in solution from under high rainfall. Ferromagnesium minerals are more susceptible to chemical weathering than feldspar and quartz. Tightness of packing of ions in crystals is yet another property for encouraging mineral weathering processes. Less tightly packed minerals like olivine and biotitic are easily weathered as compared to tightly packed zircon and muscovite, resistant. Topography and climate. Topography is an important factor in relating rocks with the atmospheric pressure, temperature, and water vapor. The climatic condition tends to control the kind and rate of weathering. Under conditions of low rainfall, there is a dominance of physical weathering which reduces the size and increases the surface area with little change in volume. The increase in moisture content encourages both chemical as well as mechanical changes. This also creates new minerals and soluble products. The rates of weathering are generally fastest in humid tropical regions as there is sufficient moisture and warmth to encourage chemical decomposition. The easily weatherable minerals disappear on account of intense chemical weathering and more resistant products tend to accumulate, such as hydrous oxides of iron and aluminum. Climate controls the dominant type of vegetation, which in turn controls the biochemical reaction in soils and mineral weathering. Rock type. The rock type determines the resistance of the rock to the weathering processes that operate in that particular environment. Each rock type is composed of a particular set of minerals which are joined together by crystallization, chemical bonding, or cementing. When the forces of plate tectonics move these rocks from the environment in which they formed and expose them to the atmosphere, they begin to weather. Rock structure. Highly jointed or faulted rocks present many planes of weakness, along which weathering agents, example water, can penetrate into the rock mass. Erosion. The dynamism and efficiency of erosion determines how rapidly any weathered material is removed, how frequently fresh rock is exposed to weathering, and if deeply weathered profiles are preserved. Time. The duration of the period that the same type of weathering has been operating, uninterrupted by climatic change, earth movements, and other factors, determines the degree and depth to which the rocks have been weathered. Physical weathering processes. Physical weathering happens especially in places where there is little soil and few plants grow, such as in mountain regions and hot deserts. The types of physical weathering include abrasion, crystallization, root wedging, insulation weathering, human mining, animal activity, tumbling, compressional stress, crushing waves, tensional stress. Physical weathering is more effective in areas which have a little vegetation, a large diurnal range of temperature, or temperatures fluctuating around 0 degrees Celsius. Abrasion. The primary process of physical weathering is abrasion. It is the process in which rock blocks are reduced in their sizes. Sand and other particles normally move above rock bodies. The mechanical scraping of a rock surface by friction between rocks and these moving particles is known as abrasion. Particles are transported by wind, glacier, waves, gravity, running water, or erosion. After friction, the moving particles dislodge the loose and weak debris from the sides of the rock. These particles can be dissolved in the water and taken away to some other location. Abrasion by water, ice, and wind processes, loaded with sediment, can have tremendous cutting power. The intensity of abrasion depends on the hardness, concentration, velocity, and mass of the moving particles. The major incidences responsible for physical weathering are expansion resulting from unloading, crystal growth, thermal expansion, organic activity, and colloidal plucking. Mechanisms of physical weathering. The major mechanisms of physical weathering include freezing and thawing, root wedging, and heat spalling. Recurring hotness and coldness is an important controlling factor in weathering. One of the main causes of physical weathering is the formation of ice in cracks or cavities within rocks. Freezing and thawing. Block disintegration occurs when rocks split along joints. This can happen as a result of repeated cycles of freezing and thawing. Freezing and thawing are the first set of processes. First, water soaks into the cracks or cavities of the rocks existing below the surface and gets sealed up. Then, if the temperature falls low enough during night times, the water freezes. When water freezes into ice, its volume gets increased by 9%. As a result of this, it expands or thaws in the cracks and may push hard enough to split the rock into minor fragments. Under specific circumstances, this expansion is able to displace and create fractures in most of the rocks. Not all volumetric expansion is caused by the pressure of the freezing water. It can be caused by stresses in water that remains unfrozen. Frost weathering. Frost weathering is a collective name given for several mechanical weathering processes induced by stresses created by the freezing of water into ice. The term includes a variety of processes such as frost shattering, frost wedging, and cryofracturing. The process may act in a wide range of spatial and temporal scales, from minutes to years, and from dislodging mineral grains to fracturing boulders. Frost weathering is mainly driven by the frequency and intensity of freeze-thaw cycles and the properties of the materials subject to weathering. It is most pronounced in high altitude and latitude areas. Root wedging. The second mechanism is the root wedging. Plant roots have a great role to play in weathering. Plants are effective agents of mechanical weathering. Roots can penetrate through the cracks of rocks to depths of several meters. As the roots grow, they exert a tremendous amount of pressure on the walls of the cracks. This breaks them into pieces. Root wedging is a major process of mountains containing forests and natural vegetation. Heat spalling. The weathering due to fluctuation in temperature is termed as thermal weathering. It is observed in almost all the climatic zones. It is more intense in regions characterized by sharp temperature fluctuations, dry air, absence, or poorly developed vegetation cover. Heat spalling is a major process of mechanical weathering. Heat from forest fires will cause the outer surface layers of rock to expand quickly and break away in spalls. Most igneous and metamorphic rocks are polymineralic, that is, composed of several minerals. These minerals have different coefficients of thermal expansion, and it causes differential expansion of minerals, thus gives rise to minute internal fracturing. Even in monomineralic rocks, the linear coefficient of expansion of mineral differs from one direction parallel to the crystallographic axis to the other. Thus, monomineralic rocks also disintegrate due to temperature changes. Rocks composed of different colored minerals also undergo differential expansion. This is due to the fact that dark minerals are more strongly heated than the lighter ones. The difference in their volumetric expansion may also lead to the development of cracks and gradual disintegration of the rock. This process is also known as granular disintegration. Exfoliation. There are two more processes of physical weathering as exfoliation and spheroidal weathering. Exfoliation denotes the loss of outer layers of rock bodies as it weathers and detaches from the main mass. This leaves a dome-like structure. Exfoliation is a form of mechanical weathering in which curved plates of rock are stripped from rock below. Exfoliation occurs particularly in hot, dry desert climates and on sheets of rock. Exfoliation domes are typical geomorphic features. In this process, the separation of successive thin shells or spalls happen from massive rocks like granites or basalts. This is common in regions that have moderate rainfall. The thickness of individual sheet or plate may be from a few millimeters to a few meters. Spheroidal weathering. Spheroidal weathering is a form of chemical weathering that affects systematically jointed bedrock that results in the formation of concentric or spherical layers of highly decayed rock within weathered bedrock that is known as saprolite. When saprolite is exposed by physical erosion, these concentric layers peel or spall off as concentric shells. Spheroidal weathering is a unique process. It is a kind of chemical weathering of systematically jointed massive rocks, including granite, dolerite, basalt, and sedimentary rocks such as silicified sandstone. It occurs as the result of the chemical alteration of such rocks along intersecting joints. Chemical weathering processes. The second major type of weathering is the chemical weathering. It is the process of decomposition of Earth's surface materials. It is done by various agents and chemical reaction. The reactions here are exothermic and result in the increase in volume of minerals that contribute to the physical disruption of rock. Effectiveness of chemical weathering. The effectiveness of chemical weathering is directly related to the mineral stability in weathering, amount of surface area exposed, which itself is exponentially related to the density of fractures in a rock. Rate of chemical weathering. The rate of chemical weathering depends on various factors like temperature, amount of surface area, and availability of water or natural acid. Impacts of chemical weathering. Most chemical weathering results in an increase in bulk with resulting strains and stresses within the rocks, formation of some lower density materials, reduction in particle size and increase in surface area of masses, growth of more mobile minerals and formation of more stable minerals. Processes of chemical weathering. The major processes involved in chemical weathering are solution, oxidation, hydration and hydrolysis, carbonation, dissolution. Solution. Solution is the process of dissolving mineral constituents by water or acid. Most minerals have low solubility in pure water, but rain contains carbonic acid, so that carbonate minerals dissolve readily in acidic solutions. Some substances present in the rocks are directly soluble in water. The soluble substances are removed by the continuous action of water, and the rock no longer remains solid and form holes, rills, or rough surface, and ultimately falls into pieces or decomposes. The action is considerably increased when the water is acidified by the dissolution of organic and inorganic acids. Hydration. Hydration involves two processes as hydration and hydrolysis. Hydration involves absorption of water, chemical combination of water molecules with a particular substance or mineral leading to a change in structure. Soil-forming minerals in rocks do not contain any water and they undergo hydration when exposed to humid conditions. Rain, streams and seawater dissolve minerals from rocks, causing the rocks to crumble. For example, water dissolves the mineral feldspar from granite, leaving grains of quartz, a mineral that forms sand. Upon hydration, there is swelling and increase in volume of minerals. The minerals lose their luster and become soft. It is one of the most common processes in nature and works with secondary minerals such as aluminum oxide and iron oxide minerals and gypsum. Some of the typical mineral weathering reactions can easily illustrate these. Conversion of hematite into limonite is a typical example. Conversion of bauxite into hydrous aluminum oxide is another example. Conversion of anhydrite into gypsum is another example. Conversion of olivine into serpentine is yet another example. Hydrolysis. Hydrolysis is also a process of chemical weathering. It is due to the dissociation of water into H plus and OH minus ions, which chemically combine with minerals and bring about changes such as exchange, decomposition of crystalline structure, and formation of new compounds. Water acts as a weak acid on silicate minerals. Reaction between mineral and water leads to the formation of a new mineral or dissolved material. Hydrolysis is the most important process in chemical weathering. It involves formation of hydroxyl ions and does not represent a chemical change. Hydrolysis of feldspar, for example, produces clay. Oxidation. Atmosphere contains 21% of free oxygen, whereas the oxygen content of air dissolved in water is 30 to 35%. These two forms of oxygen are the most active chemical agents for weathering. Oxidation of minerals and rocks is an effective process in decoloration and decomposition of materials. In this process, the atmospheric oxygen combines with the metal ions of minerals to form oxides or hydroxides. sulfide minerals become unstable and gradually substituted by sulfates. The equations of oxidation or attack by oxygen are as follows. 2Fe2SiO4 olivine plus H2O plus O2 equals FeO.OH, geothite plus dissolved silica. In the process of oxidation, the mineral geothite dehydrates to form hematite, which is a very stable iron oxide. Geothite is yellowish color, while hematite is brick red in color. Thus, rocks rich in iron oxides tend to form mainly red soils. Example, FeS2 plus 8HCO2 plus 7.5 O2 equals Fe2O3 plus 4SO4 to the power of minus 2 plus 4CO2 plus 4H2O. Pyrite oxidizes rapidly to form hematite in the presence of water and oxygen. The oxidation process is more active in the presence of moisture and results in hydrated oxides. Example, minerals containing iron and magnesium. 4FeO ferrous oxide plus O2 converts into 2Fe2O3 ferric oxide. 4Fe3O4 magnetite plus O2 converts into 6Fe2O3 hematite. 2Fe2O3 hematite plus 3H2O converts into 2Fe2O3 dot 3H2O limonite. The minerals which are prone to chemical attack are feldspars, pyroxene and amphiboles. The minerals that are resistant to chemical attack are quartz and clay minerals. Example, kaolinite. Carbonation and dissolution. Carbonation is the reaction of carbonate or carbonate ions with minerals. As rainwater falls through the atmosphere, it dissolves small amounts of carbon dioxide. The atmospheric carbon dioxide, when dissolved in water, it forms carbonic acid. Carbonic acid plays a significant role in chemical weathering. Carbonic acid is formed naturally in rainwater. Additional carbon dioxide is picked up in the ground from decaying vegetation. Carbonic acid is the principal weak acid responsible for chemical weathering. 2H2O plus CO2 converts into H2CO3. This carbonic acid attacks many rocks and minerals and brings them into solution. The carbonated water has an etching effect upon some rocks, especially limestone. The removal of cement that holds sand particles together leads to their disintegration. CaCO3 calcite, slightly soluble, plus H2CO3 converts to CaHCO3 2, calcium bicarbonate, readily soluble. The formation would be H2O plus CO2 equals H2CO3 equals H plus 1 carbonic acid plus HCO3 minus 1 bicarbonate ion. The hydrogen ion in solution, H plus 1, is very reactive. For example, it can attack feldspar and cause the reaction of feldspar with water, hydrolysis. Acidic rainwater is also very effective at breaking down calcium carbonate. Calcium carbonate plus carbonic acid equals calcium ions plus bicarbonate ions. CaCO3 plus H2CO3 equals Ca++ plus 2HCO3 minus 1. Biological weathering processes. Unlike physical and chemical weathering, the biological or living agents are responsible for both decomposition and disintegration of rocks and minerals. The biological life is mainly controlled largely by the prevailing environment. Biological weathering comprises a group of processes that are caused by or assisted by the presence of vegetation or to a lesser extent animals, including root wedging and the production of organic acids. Man and animals. The action of man in disintegration of rocks is well known as he cuts rocks to build dams, channels, and construct roads and buildings. All these activities result in increasing the surface area of the rocks for attack of chemical agents and accelerate the process of decomposition. A large number of animals, birds, insects, and worms, by their activities, they make holes in them and thus aids for weathering. In tropical and subtropical regions, ants and termites build galleries and passages and carry materials from lower to upper surface and excrete acids. Rabbits, by burrowing into the ground, destroy soft rocks. Moles, ants, and bodies of the dead animals provide substances which react with minerals and aid in decaying process. The earthworms pass the soil through the alimentary canal and thus bring about physical and chemical changes in soil material. Higher plants and roots. The roots of trees and other plants penetrate into the joints and crevices of the rocks. As they grow, they exert a great disruptive force and the hard rock may break apart. Example, pipal tree growing on walls and rocks. Some roots penetrate deep into the soil and may open some sort of drainage channel. The roots running in crevices in limestone and marble produces acids. These acids have a solvent action on carbonates. The dead roots and plant residues decompose and produce carbon dioxide, which is of great importance in weathering. Role of microorganisms. In early stages of mineral decomposition and soil formation, the lower forms of plants and animals like mosses, bacteria and fungi, and actinomycetes play an important role. They extract nutrients from the rock and nitrogen from air and live with a small quantity of water. In due course of time, the soil develops under the cluster of these microorganisms. This organism is closely associated with the decay of plant and animal remains and thus liberates nutrients for the use of next generation plants and also produces carbon dioxide and organic compounds which aid in mineral decomposition. Organisms can assist in breaking down the rocks into sediments or soils. Lichens, fungi, and other microorganisms are the typical examples. Rates of weathering. There are several factors determining the rate of weathering. The notable ones are climate, biota, organisms, time, mineral composition. Climate, which is usually measured in terms of temperature and moisture, can drastically affect the rate of weathering. High amounts of water and higher temperatures generally cause chemical reactions to run faster. Thus, warm, humid climates generally have more highly weathered rock, and rates of weathering are higher than in cold, dry climates. Example, limestones in a dry desert climate are very resistant to weathering, but limestones in a tropical climate weather very rapidly. A high temperature and high amounts of water also controls vegetation, which indirectly affects the rate. Seasonality of precipitation affects the rate of weathering as well. Organisms, biota. Animals, burrowing animals like rodents, earthworms, and ants bring material to the surface where it can be exposed to the agents of weathering. Time. Weathering is a slow process. When we speak of time in a geologic sense, millions of years are often used as the units. The bedrock of Greenland has barely been weathered, and its age is over 3.5 billion years. The longer that a rock has been exposed to the weather, the faster it weathers. Mineral composition. All chemical and physical properties are determined by the mineral composition of the rock. Mineral composition is more important in determining the rate of chemical weathering. Those minerals that are most reactive with acids, water, and air are weathered at a more rapid rate. Mineral composition also affects physical weathering. Minerals that are soft, hardness lower than 6, can be easily abraded and blasted. Slope and weathering. Slope is yet another property for weathering. On steep slopes, weathering products may be quickly washed away by rains. On gentle slopes, the weathering products accumulate. On gentle slopes, water may stay in contact with rock for longer periods of time and thus result in higher weathering rates. Porosity, faults, and shears in materials are also controlling factors for weathering. Porous sediment equals better circulation and thus faster weathering process. Impermeable rocks will mean that no or little circulation will take place in rocks and weathering will be slower. Enhanced weathering rate occurs if faults and shears are present in rocks. Exposure. Rocks that are exposed to the atmosphere tend to weather much quicker. Bedrock that is covered by soil and vegetation may not weather as quickly. Particle size. The particle size of the material can affect the rate of weathering. The smaller the particle size, the faster it will weather. The more surface area that is exposed, the more it will weather. Effect of climate. Rapid weathering occurs in hot and wet climates. Cold, moderately dry climates experience intense mechanical weathering due to frost wedging. Cold, dry climates have very slow rates of rock weathering. Weathering products. Weathering gradually weakens rocks and eventually produces new geological materials like rock fragments, sands, silts and clays that are more stable in the new environment. Weathering generally produces finer and less dense rock materials and weaker, more porous and permeable rock masses. In the tropics and subtropics, intense weathering in the hot and humid conditions produces thick weathered profiles which may be up to 100 meters or more thick. Weathering processes penetrate down discontinuities or planes of weakness such as faults and joints in the rock mass and then attack the faces of the joint-bounded blocks, penetrating the solid blocks. Weathering preferentially attacks the corners and edges of the joint blocks, causing them to become rounded. This action is assisted by stress release, which causes the rock to flake into curved shells in a process termed exfoliation. Behavior of geologic materials. Geologic materials are used in construction of buildings. These are subjected to weathering depending upon the rock's fundamental properties of hardness, durability and stability over time. Mineral weathering plays a prominent role in many biogeochemical and geomorphological processes. Soil is the ultimate product of weathering. It supplies nutrients to soils and streams, accelerates physical erosion by weakening bedrock and producing easily erodible soil, and modulates Earth's long-term climate by drawing down atmospheric carbon dioxide. The temperature and rainfall. The temperature and rainfall of a region controls the conditions of weathering. When the temperature is very low, mechanical weathering takes the lead role. When the temperature increases and the rainfall is also more, chemical processes take the lead role. Weathering is one of the major catalysts for promoting the rock cycle. It plays a very unique role in the rock cycle. Creation of soils and sediments are done by the weathering processes. Unloading. Another main type of physical weathering results from unloading. Unloading occurs when overlying materials, such as soil or another rock stratum, is removed, most commonly through erosion, and confining pressure on the underlying rock is decreased. In response, the rock generally fractures into sheets which lie perpendicular to the direction in which pressure is released. Since the most common occurrence is the removal of a horizontal layer of material above the rock, the results of unloading are often seen as sheets of rock which lie parallel to the surface topography. Conclusion. Geomorphology is the study of the nature and origin of landforms, particularly of the formative processes of weathering and erosion that occur in the atmosphere and hydrosphere. These processes continually shape the Earth's surface and generate the sediments that circulate in the rock cycle. Landforms are the result of the interactions among the geosphere, atmosphere, and hydrosphere. It is very essential to study these Earth's dynamic processes because most of our human activities are on these landscapes and landforms.